There is a planet out there that makes Saturn look ordinary. It is not a planet we have ever photographed, and it may not even be a planet at all. But something crossed in front of a distant star in 2007, and what it left behind in the data is one of the strangest light curves ever recorded in the history of astronomy. The object is called J1407b, and if the models are correct, it is surrounded by a ring system so impossibly large that it dwarfs everything we have ever seen in our own solar system. We are talking about rings wide enough to stretch from Mercury's orbit almost to Venus's, and this is the story of J1407b. The story starts with a star, a young, sun-like star sitting about 450 light-years away from Earth, in a region of the sky associated with the Scorpius Centaurus Stellar Association. J1407 is roughly the same mass as our Sun, but it is far younger, around 16 million years old. To put that in perspective, our Sun is about 4.5 billion years old. J1407 is, in cosmic terms, still a newborn. It was late 2011. A graduate student named Mark Picot, working under astronomer Eric Mamajek at the University of Rochester, was scanning the public light curve database of the SuperWASP project. He was looking for something else entirely, checking for brightness variation in young stars of the Scorpius Centaurus Stellar Association, which his team had been studying since 2009. Then he found it. The light curve of J1407 from 2007 was unlike anything in the catalogue. It didn't look like a standard exoplanet transit, where a single planet crosses its star and produces one clean, brief dip in brightness. This was a series of sharp, irregular drops and recoveries, at least 5 major dimming events, nearly symmetrical around a deep central eclipse that lasted roughly 14 days. Picot and Mamajek presented their discovery at the 219th American Astronomical Society Conference in Austin, Texas, in January 2012. The question they faced was immediate and enormous. What blocked that star? To answer that question, astronomers had to reverse engineer the eclipse. They used the light curve itself as a kind of X-ray. As the unknown object passed in front of J1407, each ring of material it carried produced a distinct change in the star's brightness. A denser ring blocked more light. A gap between rings let more light through. The slope of each transition, how fast the brightness changed, encoded the speed of the object and the sharpness of each ring edge. What emerged from that analysis was astonishing. The object responsible for the eclipse, now designated J1407b, appeared to be surrounded by a massive disk of rings. Not a ring system like Saturn's, a few 100,000 kilometers wide. This one spanned a radius of roughly 90 million kilometers. To put that in perspective, the average distance from Earth to the Sun is approximately 150 million kilometers. Saturn's rings, by comparison, span a radius of roughly 450,000 kilometers. J1407b's disk is approximately 200 times larger. Astronomers identified at least 37 distinct rings in the structure. The total mass of dust and material in those rings is estimated to be roughly equal to the total mass of Earth held in a flat, tilted disk orbiting an object that no telescope has ever directly seen. Mamajek described it plainly. You could think of it as kind of a super Saturn, but what is J1407b itself? Based on the rate at which its disk moved in front of the star, approximately 35 kilometers per second, researchers calculated that J1407b's mass is most likely somewhere between 5 and 20 times the mass of Jupiter. That places it at the boundary between a very large gas giant and what is called a brown dwarf, an object too massive to be a typical planet, but not quite massive enough to ignite as a star. Its exact nature remains uncertain. That uncertainty is, as we will see, the least of the mysteries here. Look more closely at the rings, and they become even stranger. The innermost ring extends to a radius of about 30 million kilometers from J1407b, and it is the most opaque region of the entire disk, meaning it blocks the most light. Moving outward, the rings vary in density, separated by gaps of empty space. Two of those gaps, in particular, stand out. One gap is roughly 4 million kilometers wide, located between radii of about 59 and 63 million kilometers from the center. The other is about 1 million kilometers wide, sitting slightly further in. The most natural explanation for gaps like these, and the one that most researchers favor, is that moons are forming inside them. Just as the shepherd moons of Saturn carve lanes through its rings, something orbital and massive appears to be clearing these paths in J1407b's disk. Based on the width of the larger gap, the object responsible could have a mass somewhere between that of Earth and Mars. This would make it, if confirmed, an exomoon, a moon orbiting a planet outside our solar system. No exomoon has ever been directly confirmed anywhere in the universe. J1407b may be in the process of building several. The rings are also tilted. J1407b's disk sits at an angle of 13 degrees relative to the path the object takes across the sky. That slight tilt is what gave the 2007 eclipse its nearly but not perfectly symmetrical shape. The ingress and egress times were slightly different, encoded in the light curve for anyone who knew how to read it. And then there is the thickness. The height to radius ratio of the disk is extraordinarily thin, about 1 part in 1,000. This is a structure that is essentially flat across an area spanning hundreds of millions of kilometers. The rings are thin, organized, and precise. That kind of precision implies that the particles within them are not colliding violently. They are settling, growing, building towards something. Astronomers believe that over the next several million years, J1407b's rings will thin further, and the material will gradually coalesce into a full system of moons. What we are observing, some researchers argue, is the early formation of a satellite system, a process our own solar system went through billions of years ago, compressed into a single observable snapshot. But here is where the story becomes genuinely complicated. For J1407b to be a companion of the star, J1407 orbiting it on a closed path, certain conditions have to hold. The orbit would need to make sense. And when astronomers ran the numbers, the orbit refused to cooperate. Continuous monitoring of J1407 after 2007 found no repeat eclipses. Historical photographic plates, going back to the early 1900s, including a massive archive at Harvard University that has been digitally scanned, showed no eclipses over more than a century of data. This ruled out short orbital periods and most of the near-circular orbits that would make a bound companion plausible. What remained, if J1407b orbits the star at all, was a long, highly elongated path. Researchers estimated an orbital period of roughly 14 to 17 years, probably closer to 16 or 17, and an eccentricity between about 0.72 and 0.78. In plain terms, that means the orbit is not even close to circular. At its closest approach to J1407, J1407b would swing into a distance of about 5 times the Earth-Sun distance. At its farthest, it would stretch dramatically outward, and that closest approach is where the ring system falls apart. At that distance, the gravity of J1407 would be strong enough to begin stripping away the outer regions of J1407b's disk. In 2016, researchers Stephen Reeder and Matthew Kenworthy ran simulations of this scenario and found that a ring system orbiting J1407b in the conventional direction, the same direction the planet orbits the star, What scientists call prograde motion would fall apart within just a few passes. It could not survive. There was, however, one possible exception. If the rings orbit J1407b in the opposite direction backward relative to the planet's own motion around the star, what scientists call retrograde motion, the system shows dramatically better stability. Simulations suggest retrograde rings could survive for more than 10,000 orbits. The star's gravitational tug is still present, but the retrograde configuration resists disruption more effectively. The rings, in other words, would have to be spinning backward. So that raises the next question. How do you end up with rings that spin backward? In our own solar system, rings form in the same direction that their host planet rotates and orbits. That is the expected outcome of standard planetary formation. Gas and dust collapse into a disk, and everything within that disk tends to spin the same way, like water going down a drain. For J1407b's rings to be retrograde, something unusual had to happen. In a 2024 study, physicist Wenshui Liu at Henan Normal University in China ran two-dimensional hydrodynamical simulations, computational models of how gas and dust flow around a massive planet embedded in a disk. His results suggested a possible mechanism. If J1407b formed alongside other giant planets in the early J1407 system, gravitational interactions between those planets could have thrown J1407b into a highly elongated orbit. Think of it as the same kind of gravitational jostling that, in our own early solar system, pushed Jupiter inward and reshaped the entire inner system. In J1407b's case, those interactions may have herded it into a long, narrow path around the star. Once the orbit became sufficiently elongated, the simulations showed something unexpected. The way gas and dust flow around a planet in that kind of orbit, governed by complex fluid dynamics, gradually causes the material closest to the planet to start circulating in the opposite direction. The planet gets stretched into an eccentric path, and the disk material responds by reversing course. The result, according to Liu's models, is a retrograde circumplanetary disk rings that spin backward around a planet that itself spins forward. This is still a hypothesis. The paper has not been peer-reviewed as of early 2025, but it is the first proposed mechanism that could coherently explain why J1407b's rings spin the way they apparently must, given the stability analysis. Some researchers argue the whole picture is even stranger than this, because there is another possibility entirely. What if J1407b does not orbit J1407 at all? In 2017, the ALMA telescope array, the Atacama Large Millimeter Array, located in the Chilean desert and one of the most sensitive radio observatories ever built, was pointed at the J1407 system. Astronomers were searching for direct evidence of the ring system in the form of thermal radio emission from dust particles. What they found was puzzling. No object appeared at the location where a gravitationally bound companion would be expected. But there was a faint radio source detected at a confidence level, suggesting it was real, located at an angular separation from J1407 that was too large to be explained by a bound orbit. At the distance of J1407, that separation corresponded to a projected distance of 61 astronomical units, far beyond any reasonable bound orbit. However, and this is the critical observation, the position of that source was roughly consistent with where a free-floating object would have moved since 2007, traveling at the same velocity measured during the eclipse. If J1407b is not orbiting the star, but instead drifting freely through space, and if it happened to pass between Earth and J1407 during those 56 days in 2007, it would have continued moving in a straight line. The 2017 ALMA source was located approximately where that line pointed. This is the free-floating hypothesis. J1407b, or whatever object produced the 2007 eclipse, may not be bound to any star. It may be a rogue substellar object, wandering through the galaxy, carrying its enormous ring system with it. The implications are startling. A free-floating body with a ring system this size would have no Hill sphere, no gravitational domain defined by proximity to a host star. Its disk could be much more stable than any bound companion model allows. The retrograde problem may not apply at all. But the 2017 ALMA detection was not confirmed. In 2024, J1407 was observed again by ALMA. The results, published in 2025, found no object at the expected position. The 2017 source had either moved beyond detectability, dimmed substantially, or, as the researchers cautiously acknowledged, was a noise spike all along. The data could not distinguish between these possibilities. What the non-detection did establish was a constraint on the disk itself. Whatever material surrounds J1407b, it is not dominated by dust particles larger than about 1 millimeter. A thick disk of large grains can be ruled out. A thin or flared disk of smaller particles remains consistent with all observations. The object is still missing. Here is what the data confirms. In 2007, something passed in front of J1407 and blocked up to 95% of its light for 56 days. The shape of that eclipse is consistent with a massive, ringed, substellar object moving at roughly 35 kilometers per second relative to the star. The ring system, modeled from the light curve, would span a radius of about 90 million kilometers and consist of at least 37 rings, with gaps that suggest ongoing moon formation. The total mass in those rings is comparable to the mass of Earth. Here is what remains uncertain: whether J1407b orbits J1407 at all, whether its rings rotate backward, whether J1407b is a gas giant or a brown dwarf, whether the moons implied by the ring gaps actually exist. No telescope has directly imaged J1407b. No second eclipse has ever been recorded. Every model that fits the 2007 data creates new problems that require additional assumptions to solve. Astronomers have been monitoring J1407 every clear night through the American Association of Variable Star Observers. Amateur observers around the world contribute to that watch. The next eclipse, if there is one, could begin without warning. When the star starts fading again, the geometry of the ring system will snap into focus almost immediately. That moment has not yet arrived. In the early 1600s, when Galileo first turned his telescope towards Saturn, he described what he saw as ears. He could not resolve what he was seeing. The rings looked like flanking shapes attached to a planet that should not have them. It took decades of improved optics and careful observation before the true structure became clear. We are, in some ways, in a similar position with J1407b. We have seen its shadow. We have measured its speed. We have mapped the rings it carries, dozens of them, and found within those rings the hints of worlds still forming. We have debated whether it was ever really there, and searched for it across 17 years of follow-up observations. And it has not come back.